Okay, guys. So today is supposed to be the last lecture, right? I think that most of you are excited about that. Okay, so we will be discussing. Um, we will continue actually the channel equalization, and then we will speak about the final exam. Okay. So we discussed last time the types, how to mitigate the interference or the fading, the different type of fading, and then we spoke about the diversity itself, and we named it diversity, and we discussed like 5 types of this diversity, which is the concept of diversity is to repeat the information several times, okay? And the main condition is once you repeat this information, you need to make sure that each of this repetition experience different environment, different noise, different interference, different fading. Because if your repeated information or your repeated sequence experience the same noise, in this case there is no meaning for diversity or there is no meaning for repetition. Okay, and we discussed how to repeat the information. We had like 5 types. We can repeat the information based on the space. We named it space diversity, and we discussed the condition that to make sure that these independent channels can be happen if you have the space between the antennas more than half of the wavelengths, and we discussed this half of the wavelengths is something maybe symbolic, right? Because it depends on the environment itself. And once we said that we can have more antennas, so something jumped in our minds that we have transmitter, we have receiver, we have antenna as a transmitter, we have antenna as a receiver. Which antenna we should like repeat, right? So in this case, there is 3 types arised here. We have traditional system is like SISO, we have single input, single output. If we have multiple antennas at the receiver side, we have SISO, single input, multiple output. If we have multiple antennas at the transmitter side, we have MISO, which is multiple input, single output, or we can do both, multiple input, multiple output, which is a common thing in modern communication, which is MIMO. And we discussed different techniques for combining selection, select the largest, like maximum ratio combining, and also equal gain. And we said that we can arrange them based on the complexity or the performance. Okay, so complexity, the best one is selection combining, the worst one is maximum ratio combining. But for the performance, we have the best one is maximum ratio combining, the worst one is the selection combining. Okay, and then we discussed, instead of repeating the information based on the space, we can repeat it based on the time. We have time diversity. We discussed it like you wait certain period and send another copy of the information, and you need to wait the period of coherence time, and then we have another time which is a frequency diversity. We need to wait or to have subcarrier separation of the coherence bandwidth. And then the last 2 types of this diversity we were discussing angular diversity and polarization diversity. Okay, and then we jumped directly to the channel equalization. Instead of mitigating the fading using diversity techniques, we can do some kind of equalization, right? Because all the bad things happen inside the channel, so we can actually do what is called the channel equalization to equalize the effect of this channel. And we discussed, we have many types of equalization actually. We just we will be discussing a few here. We discussed linear equalizer, which is zero forcing and minimum square error. And we discussed zero forcing, that you, like, ideally you force the interference to be zero ideally, but unfortunately it's not this not happen in zero forcing, and we can do this by multiplying the received vector by the inverse of the channel itself, okay? And the inverse of a channel itself, typically if you have a channel with a square channel, in this case, or a square matrix, in this case you can use inverse directly. If not, which is the most common in wireless communication, because the dimension of this channel is number of transmit antenna times, or number of receive antenna times the number of transmit antennas, okay? So typically in modern wireless communication, we have the number of receiver antenna is higher than the number of transmit antenna. So typically we have H is not a square, okay? In this case we use what is called, instead of inverse, we use pseudo inverse, but the same concept of multiplying this equation or the received vector by the inverse of a channel directly. And we discussed that zero forcing will suffer from noise enhancement because typically the channel coefficients are very small, right? And once you divide this equation by H, or you multiply it by the inverse, in this case this noise will be divided by a smaller values, which will cause enhancement for this noise. Okay, one of the option is to make sure that these values will be greater than, it's not a small value, so it's greater than 1, so we will use minimum square error, okay? And we discussed, this is linear equalizers, and we discuss this in more details about the equation. Here, this equation that guarantee that the noise enhancement will be reduced, okay? And we discussed like a few examples, how to calculate. You just plug in the rule and like you do some kind of matrix multiplication. So you must be aware of how to find the inverse, like how to do these kind of operations. Okay, and we did the same thing for minimum mean square. Okay, so today we'll be discussing a maximum likelihood, and what is called another thing is a rack receiver. Okay, so both of them, maximum likelihood and rack receiver, is a non-linear equalizer. Okay, so for linear equalizers we have zero forcing, we have minimum square error. For non-linear equalizers, I just brought these two types of equalizers, but again there's another tens of equalizers you can find. Okay, so maximum likelihood is the best or the optimal optimizer or the optimal equalizer in digital communication for uncoded signal, okay? Because there is another branch is called coded signal, but we don't care about that, okay? So I'm trying to be accurate because I know that some of you are research students, okay? So anyhow, so maximum likelihood is the most accurate or the optimal decoder in wireless communication here, okay? And it came from its name, like maximum likelihood, like maximum likelihood. And this idea came naturally from, if you go back very far to, let's say, okay, so module, maybe, okay, it's not here, module 3, when we discussed, okay, so it's in module 3, for sure. Okay, so when we have, like, when we divided, suppose that we transmitted 4 symbols, okay, and we have like 4 regions, okay, and these 4 regions, the boundary zones, and we said that we can actually be careful of this here, right? So if you remember from the 3rd module, when we have a scatter plot, and we said that suppose that we transmitted 4 QAM, okay, and we have these 4 symbols. Okay, this is the ideal positions for the received vector, right? So typically, if we don't have any noise, we will receive the symbols here, right? So this is S1, this is S2, for example, this is L3, this is S4. Typically, the arrangement is not like that. This is they follow. If you are make some coding, you are following what is called a gray a gray mapping. Okay, so for gray mapping, this is S1, this is S2, this is S3, this is S4. But anyway, okay, we don't care about that. So S1, S2, S3, S4. This is just for symbols. Okay, so typically you have a received vector like here. And what we discussed, if you remember, we have like a yellow symbol, a blue symbol, black symbol, whatever, orange or red symbol, if you remember. And for example, this is the boundary zone of the first symbol, right? So if I receive the signal here, I will say that this is most likely will be S1, right? Remember that? Okay, what we did that last module. Or if we receive a signal here, so we will say that this is most likely will be here. And we said that, and based on that, we calculated the error and we formed the threshold decision. So this you might send S1 here, okay? And instead of receiving it in here, in this zone, you might receive it outside the zone. Okay, and this will cause an error, right? We discussed this in more detail. Okay, but the question here, I'm saying this one here, you receive this one here, so most likely it will be S1. But mathematically, how can we decide this one belongs to S1? We said that logically, right? In last module, we didn't drive or we didn't see any formulation, because typically the computer program does not think logically. You need to program it, right? You need to write an algorithm in order to execute it, okay? So by your naked eyes, if you receive this vector here, you will say that this one, most likely, it was S1, right? But how can we transform this into a mathematical form? Actually, this is the concept of maximum likelihood. Okay, so maximum likelihood, once it sees this one here inside this boundary zone, it says this symbol most likely, or maximum likely, most likely will be S1. Okay, so how can we do this? Simply, we measure the distance. Okay, so like for example, the distance between this is, let's say this is R, the received signal. Okay, the distance here, let's say it's called RS1. Okay, and the distance here, okay, this is R, S4. And another distance here, S3. And another distance here, S2, okay? Or instead of saying distance, we can call it error. Why it's error? Because typically, I must, without any noise, I must receive this point at one of these 4 points, right? I might receive it here, exactly, without any distance. I might receive it here, I might receive it here, I might receive it here, not anywhere around. Okay, so in this case, I can call this as error, right? Okay, because this is not the typical point I should receive. So any shift around this, for sure it's error, right? So I can, instead of saying RS1, I can say it error from S1. Or here, error from S4. And here, error from S3, here error from S2, okay? And because of distance, they call it Euclidean distance or Euclidean error, because it's distance for error. And logically, you have now 4 values of errors, right? And which one you will select? Based on maximum value of error, so after you calculate the distance, right? Or the error between this one and that one, you have ES1, ES2, ES3, ES4. Okay? I have a value, a certain value, as we will see, a certain value. We will see an example. Okay? So which one you will select? Right? So suppose that I have this distance is 0.215, and as an example. I have here 1.035, any number, right? 2.13, 0.75, okay? So this is the error or the distance between the received vector and the original symbols, okay? So which one you should receive, or which one you should decide based on these numbers? You will select the maximum or minimum or in between? Yeah, just try. Minimum, right?
Minimum.
Because I'm speaking about error, right? So for the best case scenario, this one must be on this one, which means that the error will be 0 and it will be great or large for the rest, right? Okay, so this is exactly the conversion of when you see this one here, by your naked eyes, you decide that this one is very close to this one, so this one is most likely you send S1. This is exactly what you did. And this is exactly the concept of maximum likelihood. Maximum likelihood set up the distance. This is distance, okay? So to measure the distance between any two nodes, but this, remember, these distances like came from a vector, right? Because this is a vector. Okay, so the distance is the norm square. I'm sure that you are familiar with norm square, right? Okay, so norm square you can like subtract and take the value like square plus value square and so on. You can. This is like a normal operation. So here, this is a distance. This is a measuring of distance. Okay, and here what I'm trying to say, I tried to find here, this is R, the received vector, minus, okay, or like Y minus HX, okay? This is Y, which is the received vector. Here, this is Y, this is Y, okay? So HX means this is X because like typically Y, originally HX plus noise. Is it correct? This is from the received vector, right? So this is the original channel, and this is the actual transmitted symbol you transmit, and this is the noise, right? Okay, so ideally, if I don't have a noise, then if I multiply X or H by the right X, suppose that I transmitted S1, okay? So S1 here, I actually transmit S1, but at the receiver side, I never know which S I transmitted. I should try all four possibles, okay? So if you calculate the error and you replace here, this is the received vector, right? And you have here minus HX, right? Norm square. Okay? So this is Y. This is Y. Y, which is HX, the actual X you transmitted plus noise, minus HX, okay? So all you need to do is try one more time X to be S1, okay? And if you look at, and if X1 here was the actual transmitted one, this term will cancel this term. And the remaining will be the noise, which is a small amount. But if you try wrong symbol here, and instead of X here, you try S2, in this case, the error will be HX minus, you cannot take this one with this one. In this case, you will have a bigger value of error. And the same thing if you tried this symbol, if you tried the fourth symbol, and so on. Okay? So what we do here is similar to you are searching for a certain value over a four possible combination or a four possible symbols, right? This is what I'm doing here. You are finding who is minimizing this equation when you are trying X to be one out of the four possibles here. If I have 8 symbols, I will have eight possibles. If I have 2 symbols only, suppose that I send 2 symbols only, 0 or 1. In this case, I will try this X, one of these 2 possibles. In our situation here, I have 4 possibles. So X belongs to S1, S2, S3, S4. The 4 symbols here I have. S1, S2, S3, S4. This is the translation of this. And I'm trying to find the argument, the X, that will minimize this equation. Okay? So typically, this is exactly what we discussed in the third module when we said that this one is most likely S1. This one, or the received vector here, if I receive the vector here, this received vector is most likely S4. Okay? The translation of it is maximum likelihood and based on this equation. Okay? So any question so far? So typically this provides the optimal bit error rate or the optimal error performance, but it's very complex. If you see the complexity, actually you calculate here like big operation, as we will see, right? Like you might think that this kind of calculation is more complex, okay? But again, suppose that you have 16 symbols. Most of the modern communication has like 64 symbols, okay? So yes, I have 64 symbols. This is not easy to calculate, for example, but for zero forcing and minimum mean square error, you just calculated it once. But for maximum likelihood, you need to repeat this equation 64 symbols. And with each time, you need to make multiplication here for matrix, subtraction for these 2 vectors, and after that you take a norm, and all this calculation is just one option to find one error. And if I have 64 errors or 64 symbols, I need to calculate 64. And this might be per one user. What about if I have multiple users? What about if I have multiple antennas? So it's extremely high, okay? But again, this is the optimal performance, the best performance ever. However, the complexity is super high, okay? Okay, so let's solve this example. Let's say I have this channel matrix, okay? So let me do this one. Okay, so suppose that I have this example. I have given the channel matrix and I have the received vector, okay? So typically, using these two information, I can calculate zero forcing, right? But I cannot calculate minimum mean square error, right? Why? Because I need the variance to calculate the minimum mean square error, okay? But here I don't care about the variance, but I care about the modulation technique itself, right? Because of the modulation technique, I can assume that how many symbols you have, okay? But if I give you these 4, or like the symbols here, suppose that I have 4 symbols here, right? X1 is -1, -1, X2 is -1, +1, X3 is like, this is typically the Fourier, okay? So suppose that I give you extra sigma here, okay? So from all this information, you can calculate the expected or the estimated symbol using zero forcing. You can estimate the expected symbol using minimum mean square error, and also you can expect the symbol from maximum likelihood. Okay, so I have the channel, I have the received vector which contains the actual noise, the actual symbol plus the noise, and I have the 4 possible symbols I sent already, okay? So I need to find minimum square error. Okay, so all you need is to calculate the distance, okay? So I will try the first possible. I will try to write in the equation, I will try to write down x1, okay? So as you can see here, I think I might freeze this one. Freeze here. Okay. Okay, so because I need the formula here, so as you can see here, this is the formula I have. And all you need is to set up y minus hx, okay? And for each x, I need to try to put x here instead of general x here. So for here, I have y minus hx, so I have h, I have y, and then I find norm square. I got the error here is 8.08, right? So, and for x2, when I try symbol 2, I got the error is 3.28. When I try x3, just like you plug here, you have y minus h, so this is constant numbers here, but you replace x with the new x you are studying. For example, if you are caring about x3, so you replace x3 here or x here by x3, which is a positive 1, negative 1. Okay, so and you got an error which is 1.48, and for x4 is 0.68. Okay, so you got 4 errors. You got 4 errors. So typically, which error you will select? The minimum one. Okay, because the minimum one will be very close to that symbol. Okay, so when I tried x4, I got like more closer or the lowest error. In this case, I know that x4 is lying in the boundary zone of x4. Okay, so I can decide that the minimum Euclidean distance, okay, or the minimum error is corresponding to x4, which is positive 1, positive 1. Okay, so the estimation or the estimated symbol from maximum likelihood is positive 1, positive 1. Is it clear, guys? Yeah. Okay. Okay, so this is actually the maximum likelihood, which is commonly used. Typically in modern communication, they used it as the baseline or the best performance you can achieve, but it's due to its complexity, it's not a practical one, especially with high dimension systems, okay? Okay, so the last thing we will be speaking about today will be RIC receiver, okay? And this RIC receiver was a very popular receiver in maybe 3rd generation when we had CDMA, okay? But still currently used in military application, because in military applications he's still using a CDMA because CDMA is more secure than the current modern communication. But anyhow, so for RIC receiver is a type of radio receiver designed to counteract the effect of multipass fading in wireless communication, especially frequency selective. Okay, so if you remember frequency selective channels, we have the frequency band or the bandwidth of the signal is greater than the coherence bandwidth, if you remember. Okay, so here in RIC receiver, it applies a very simple trick. The trick is, instead of dealing with the whole bandwidth or the whole time, because I might deal with, I divide the whole bandwidth into a small steps or a small periods. okay, and I will equalize this small part of the signal independently, okay? So in this case, for example, okay, so I might explain it here. A basic concept or a logical concept is, suppose that I have like this signal, right? This signal, okay? I got this signal. And this signal, if you try to find or to equalize this signal directly, it will be very difficult, okay? Because you need to find the transfer function. If I consider the channel, this is the channel, as a transfer function, right? And you need to find the transfer function which causes this kind of distortion. And once you find this transfer function, you equalize it, you find the inverse of this transfer function, and then you equalize the signal, okay? But here, in frequency selective channel or this type of a channel, so dealing with the whole signal is very difficult, okay? So what we are doing here, the RIC receiver, is we can actually try to take parts of the signal, right? So like a small, like this, I can handle this, equalize this separately. And then I can equalize this separately. I can equalize this separately, and so on. So you divide the signal into a small fingers, right? They call it finger or rake, okay? Or tape, right? Tab. So it can be finger based on the text book you are reading. So you might hear this is a finger, right? So this is finger or tab or rake, each slice, right? So I can slice the signal into a small slices, and I can equalize this only. And instead of equalizing the whole signal, I can equalize this one, I can equalize this one, I can equalize this one, okay? So, and after I equalize each of these fingers, I can combine them together, and then I have a final symbol or a final signal. This is actually the explanation here, how it works. So we receive the signal, okay? First of all, we receive the signal that came from multipass, because each of these signal came from a different multipass, because like I have a path, right? If I have all this signal came from one pass, I expect that the behavior will be the same. But unfortunately, this came from the first pass, this came from second pass, this came from the third pass, because it's delayed, right? So each one has different effect. That's why you see this behavior is not constant or not flat. So I receive the signal that capture all multipass component with a certain delay window. Okay, so I take each one and then I delay, because this come after that, right? So I have another delay and I deal with this one here. Another delay and I will deal with this one here. Because typically this is the time. This is the time domain, right? So this tape or this finger happens in a time duration compared to this one, right? So if you need to take this part only, you need another delay, and then after one delay you have you deal with this component, another delay you deal with that component, another delay you deal with that component, okay? So you need actually, and each of these ones has certain delay, because remember, for multipass, I don't know, I'm not sure that each replica will come periodically, right? So I might have, if you remember correctly, like this is the first copy and maybe this is the second one, maybe the third one is here. So the duration between the multipass components might not be equal, right? So, and the same thing actually, this is, let's say this is T1, this is T2, the delay 2, delay 3, and so on, based on the channel itself, okay? So, and then this is called a finger or sub-receivers, because I take each of them and try to do the receiving or demodulation for this part only after equalizing it. So each of this one consider be as a separate receiver, you equalize it, and you do a receiving, like detection. Okay, so this is what I'm saying here. So you do finger, like sub-receiver assignment. So each finger is assigned to different multibus component, okay, with a unique delay, not equal delay. And then after you equalize it, each finger perform matching filter or whatever, like you're doing the receiving part, okay? And then at the end, you do the combination. After you have a complete receiver for this part, and a complete receiver for that part, a complete receiver for that part, you combine all of them together in one signal, okay? And actually this is the form of the equation itself. You gather, you combine, this is the combination, you combine the whole received signal, but it delayed. So from 0 to L, L means that number of delays, okay? So like for example, if this rake receiver has 4 fingers or 5 fingers, in this case I have L equals 4, from 0, 1, 2, 3, 4, right? So like 5 takes or 5 fingers, okay? So I have here from 0 to L minus 1 number of fingers, okay? And for each one I will multiply it by different weight. Remember, this value of the signal will be multiplied or will be equalized differently than this one. It will be equalized differently than that one, and so on. In this case, I will have different weight to the received signal delayed by tau L, okay? So this is the typical equation for rake receiver, and actually this is the rake receiver itself. As you can see here, this is very simple. As you can see here, this is the received signal. The received signal comes here, and with 1 over W, like I have 1 over W means time, right? So because W is in frequency, okay? So I have one delay here, another delay here, so I have the first component without any delay, which is this one, okay? And another component after a certain delay for the second one. And this one is the third delay, and so on, okay? And for each one, I have a complete receiver, okay? So forget about this one here. You can, like, if I ask you about rake receiver, you can, after that, you can have here receiver or demodulator 1, okay? So, like, don't plot all that, right? So here, W1, after that, I have all this is a receiver. See here, it's just receiver. So you can write a block here, receiver, and here another receiver, here another receiver. And after that, I combine all of them, and like using combination technique, and then I go to detect, okay? So the concept actually, if I ask you to plot rake receiver, what you will plot? It's just here, 1 over W, which is the first one here is receiver 1, another W here, receiver 2, another W, 1 over W, receiver 3, and so on, okay? And all of that, after all of them, like you make a combination, and that's it, okay? So this is the concept of it. But here, because this is what the textbook wrote or draw, because instead of receiver, I have this one here, okay? So, but I don't care. I need you to understand the concept, okay? So this is typical receiver for or typical application for selective channels, okay? So the advantage for it, actually it compare the multibus fading, especially of course for selective channels, and for sure it improves the performance, reduces the error, and it was widely used in the 3rd generation. So 3rd generation is gone now, right? So typically it's currently used in military application because it's based on wideband CDMA, okay? So still actually military application because this one is very secure compared to the modern communication. Okay, but at the expense of the bandwidth or whatever, so you get something and you pay another thing. But the limitation is, as you can see here, require accurate estimation of the delay of the channel. As you can see here, as I mentioned that the duration between this replica and that replica is not equivalent, right? So it's not equal. So in this case, I need to study the behavior of the channel very carefully. I need to be accurate about this channel estimation, okay? So after I estimate the behavior of a channel, I will build these weights or these delays based on this kind of estimation, okay? So in this case, actually, I need accurate estimation of the delay and also for the channel coefficients. And also, if you didn't accurately estimate these durations, unfortunately, you will degrade the performance completely, okay? And as you can see here, it's very complex, okay? Because suppose that this is one receiver only. This one receiver can be used for a whole signal in a different equalization technique, okay? So one receiver, if I have, like, for example, 10 taps or 10 fingers, how many receiver you have here? You have 10, right? So instead of having only one receiver circuits, you have 10 receiver circuits, okay? So you actually complicated the cost of the receiver. Okay, guys, so now we're done with curriculum. So, any questions so far? Before we go to, okay, so any question regarding here? Okay, so yeah, if you've been asked about rack receiver, don't complain about the time. You don't need to go this flow. You just need to do this. Yeah.
For the MLSE,
Yeah.
so like the ticket equalizer, if two of them are equal, or like the lowest two are equal, then
Okay, if I have like so, okay, so this is a good question. So your friend asking if, like, for example, I have error 1, error 2, error 3, error 4. As an example, if I have 4 errors, okay? So the first one is 1.2, the second one is 0.3, the third one is 1.6, the fourth one is 0.3, okay? So in this case, I have 2 errors from symbol 2 and symbol 4, like the error is equivalent, okay? So this means that if we plot here, this is S1, this is S2, this is S3, this is S4, right? So this means that I have maybe a symbol, let's say this is 2 and 3, let's say this is 2 and 3, right? So I have a symbol comes here, exactly, on the border line. In this case, this distance equals this distance, okay? Or these two, okay? So in this case, the decoder will decide like either one, because I cannot decide on the marginal, I cannot on the borderline exactly, which is very rare to happen in the practice, but it can happen theoretically, right? So once you have one here, logically, you can assume that it might be here, it might be here, and you have 50% chance to be right or 50% chance to be wrong, okay? Okay guys, so let's talk about the final exam. So before we go to so before we talk about final exam, next semester I will be teaching machine learning course. Okay, so it's not listed yet. So there is the department will EC department will open 2 machine learning courses. Okay, I will teach one of them, and another one will teach another one. So my courses will be offered as a special topics for grad and undergrad students, and actually it will be suitable for maybe for research students who has no background about machine learning and would like to publish or to work heavily in machine learning. Okay? And even for undergrad students who are trying to take or to do graduation project in machine learning. So the course, my course will be called Applied Machine Learning and Neural Network. Okay, because there is another course will be offered which is Advanced Neural Network or Advanced Machine Learning. So my course will be Applied Machine Learning. It's not listed yet, okay, but it will list maybe, I'm not sure when, but it will be open for spring. So this Applied Machine Learning, it will be like half practical, half theoretical. So we will focus on understanding the machine learning, how to design a machine learning, how also can you calculate the complexity, number of additions, multiplication of the neural network you have. So typically I was teaching this course for privately for my research students. But now I will be teaching this course publicly. Okay. So if you research, you will need a machine learning course or machine learning in general. So I think you might register in this course. Okay. So anyhow.
Sorry.
Yeah.
You said spring or fall?
Fall. Sorry. The coming semester. Right? The coming semester.
Do you know which days it's going to be? I mean, the schedule?
No, because the schedule is not, typically the schedule came from the admission itself, because for example, I don't prefer actually the latest schedule, like today. Again, they do a hard job actually, because the students registered in the course, they might have some conflict with another courses. So they do a hard time job or optimization job, right? So to avoid the conflict as much as you can. So it's not, I just informed about the schedule similar to you. Yeah. Okay, so yes.
Are you taking any courses in the weekend?
No, I don't teach it. Yeah.
Is it possible?
I stay home.
Is it possible to
I
take
just do the results. Yeah.
this remotely? Because we're gonna be on WhatsApp undergrads.
Well, so I will try also to record, right? So it will be in class, in person, right? But again, it might be like one day or maybe, because it will contain labs. Labs is not like typical labs. You attend the class and you have like labs mean that I will give you a code, and this code like neural network, like feed-forward neural network, for example. And I need you to understand how to tune the hyperparameters, right? So in this case, I will give you the code, and I will try to explain, and then you try this at home, right? And you give me the report of what you got. If you change this parameter, what the outputs you got, right? So this is called a lab. It's not typical lab you attend here or something like that. So in some situation, you might find it's you maybe, for example, if next day is a lab, then it might be online or something like that. It's not, but the course is in person, and also I will record the course, because especially for machine learning, it's very hard to remember, right? Because it's most about, there is some kind of understanding, but there is some kind of practical situations you cannot memorize. You need a video or a recording, and you stop it and you try, and then you stop it again and you try. So I will make sure that I will post all the recordings. Yeah. Okay, so any questions before we go to the final exam? Okay, so let's go to the final exam. Okay. So it's not midterm. Okay, so for the final exam, it will be the total marks will be 100, but the actual weight for it is 40%, and it will be Monday, August 4th, right? Is it correct?
Yeah.
Okay, so and the time it will be 3 hours exam. However, like this is the 3 hours period, right? Because like for example, during the midterm, I give you extra time, right? If you remember. But for a final, I might not be there. Okay, the TAs might be like another TAs, I don't know, right? So typically the duration will be 3 hours. However, I will design the exam to be solved for average student to be solved in 2.5 hours. Okay, so in this case you might have 30 minutes extra to solve it. If you studied like again, I mean a well-studied student or a well-studied means that you need like to, if you spend a lot of time thinking, trying to remember what the difference between time diversity and frequency diversity, then you will, after the exam, you will complain about the time. But like, if you studied it very well, and once you see it, write it or solve it, because the exam, as the midterm exam, it was direct, but it was long, right? Because you need to find a trick. I can give you like short exam with a lot of tricky things that makes you like think or overthinking, or it might be like direct but like long, right? So if you study it very well, I think you will, most of you will finish it in 2 hours. Most of you, like if you but if you try to think, what was the analog digital communication, what's the difference between these two, like then you will waste all your time. And again, as we will discuss the type of the questions now, for the comprehensive questions or discussion questions, focus on the keywords, okay? So because I need to test you about understanding, okay? Not like you discussing, for example, the time diversity. If I ask you, for example, about the time diversity, okay? So I don't need to explain one slide with 100 words. Just give me the perfect keywords, but make sure that this is the right keywords, right? Okay, so for example, I need the separation, right? I need to repeat over time, different times. Okay, I need also to make sure that the time separation is greater than the coherence time, right? And this is the keywords, and that's it, just like in a few words. So I don't care about the rest. If you understand these two keywords, I don't care about the rest, okay? So try to be smart. Like if you have a questions, one like longer than the other one, start with the smaller one. In this case, you will release some kind of pressure, okay? So similar to the midterm exam, you will solve inside the questions paper, right? So after each question, or every question, you will have a space, you will be given a space to solve it, right? And I'm sure that this given space, you can finish the question, okay? If you need more, you might write behind, right? Behind the paper, right? And just make sure that you write to me that the rest in behind the paper or back the paper, okay? Anyhow, because again, I might not be there. So, okay, and the room, it will be this room. Okay, so and again, please follow the directions because this is the exam committee that will handle you, give you cars, whatever. So I don't know about these directions, so you must follow their directions about the arrival, about the seating. Okay, so make sure to follow the directions. And again, cheating policy, as you know, the tolerance, like simple calculator, so very simple, similar to the midterm exam, and you will be, some people or the examiners will check you, okay, before you. Okay, so the exam structure, which you are looking for, you will be given a formula sheet, okay, so this formula sheet, I will be post all that, right? But anyway, I will be posting this video. Okay, so the structure here is the formula sheet. You will be given a formula sheet. This formula sheet, I will add more rules. It will be similar to the midterm one, but I will add some extra formulas. I will post it before, for sure, like maybe in the coming couple of days after I completely finish the exam, okay? And if you didn't find a specific rule, and this rule is like easy to remember, you need to memorize it, okay? Okay, so like, for example, the capacity, I gave you a problem about capacity. And the capacity in the midterm exam, the capacity is C equals, the capacity equals the bandwidth, log to 1 plus the signal to noise ratio, okay? So, I don't think I will provide this rule in the formula sheet, okay? So, in the formula sheet, you will be given some formulas, and the rest you should memorize. Other than that, it's a very big formula, so I don't think you need to memorize it. Anyway, so the total number of questions will be 6 questions, but again, because of this is 3 hours exam, so the question will be fast. No worries, guys. It will be direct similar to the midterm exam, okay? So once you study the lectures, once you study the slides, you are fine. Totally fine. Okay? Okay. So again, it will be question style, discussion based, block diagrams, problem solving. Again, guys, I need to test you. Understand you understood it. I don't need to challenge you at all, right? So I need you to study what I gave you, and that's it. You will be fine. You don't need extra resources. You don't need anything, but you need to focus in each single word I wrote, okay, or I explain. Okay. The modules, like the second module will be eliminated completely, which is probability or random, right? So, but some rules you might need from it to like in module number 3, right? So, anyhow, so for the first module, you expect 1 question, and I gave it a small weight because you already examined about it, you already studied it in the midterm exam, okay? So it will be 15 marks. If you didn't need to study it, and forget about 15 marks, 15 marks is up to you, okay? But anyhow, it will be 1 question, and it will be 15 marks. And the third module will be 2 questions, 40 marks. It can be included the problems from the first before the midterm exam or after, but the majority will be after the midterm exam. Okay, so the majority of these 2 questions, it might be 100%, it might be 90%, it might be 80%, but not more than that. Okay, so like 80% or higher, it will come from the part that after the midterm exam in the third module. For the first one, which is the longest one, we will have 3 questions, and the total marks will be almost like 50% or 40. Okay, so again, block diagrams, discussion questions, and also problems. Okay, so be prepared for that.
question. When you say block diagrams, you want us to explain the block diagram, or you want us to like draw a wall
according
picture?
to the question, for example, if I told you draw the block diagram, okay, so it's draw.
Sure.
Yeah, okay. Draw and explain. So I will be very clear about that, okay?
Yep.
So guys, again, my questions are straightforward. I put it as a straightforward. So don't think behind the question. Okay? Explain. Draw, draw, right? Okay? So I just need, again, not to challenge you, I just need to test you understood this part, and that's it. Okay? Yeah. So, any questions, guys? Again, just study and don't even try to cheat. Okay? So, yeah. Any question? Okay, guys, good luck. And again, the exam will be. See you next semester.